All right. It is my distinct pleasure to welcome Ed Wu from Niantic. Ed is the senior project manager up in Niantic in the Seattle office. He's the manager of the Seattle office, the technical lead of Pokemon Go. And what's really great is that this sort of gives you a sense of how quickly time flows by. But Ed was an undergraduate here. He graduated in 2004. We had a lot of fun taking 125 and playing games there. And it's just really great to see him sort of go out into the world and do something so incredible like Pokemon Go. And he's going to tell us what it's like to actually run a PlanetScale platform for something like Pokemon Go.
Awesome, thank you.
Thanks, Ed.
So let's de-sleep the computer. All right. So hi, I'm Ed Wu. I'm a senior product manager at Niantic, and I'm actually head of the Pokemon Go engineering team, both the client and server. I'm here today to talk about how at Niantic we've actually created what we believe are the first generation of truly mass market augmented reality products. And I think I will go into detail here, but the key thing there is planet-scaled. They are planet-scaled shared augmented realities. And I think the way that we can start with that is with the products that I'm going to talk about. So in particular, I'd like to talk about my experience building and engineering Niantic's two seminal products, Ingress, which was initially released almost 4 years ago while Niantic was actually an autonomous unit within Google, and then Pokemon Go, which was released this past summer, and which has since been downloaded more than 500 million times. For the uninitiated, both of these games are massively multiplayer, location-based games that you play on your mobile phone. So the key element is that they overlay a single consistent reality on top of the real world for all of the users who are playing the game. So that is, every game element that I see is mirrored, not only in my game client, but in the person next to me and the person next to her. And the result of any one user's actions is then reflected on the clients of everybody around them. And so you might ask at this point, okay, so games are games. Why do people think that these particular games are such a big deal? So I want to start out with a quote from our current Surgeon General from a talk that he had just a couple weeks ago, actually. So he talks about the most common pathology in America we have in America is not heart disease, it's not diabetes, it's not cancer, but it's isolation and loneliness. And this is in the context of a year-long campaign that the Surgeon General has been conducting to try to get people outside and walking, to get people to think about their cities as walkable, design their not only at a personal level, but of getting out and walking, but also to think about how you can structure your communities and your cities to be more walkable. And but it's interesting here that he's not talking about the particular physiological gains that you would get from walking. He's talking about the root causes of why people don't get outside. And he goes on to say that one of the most interesting lessons that we can take from Pokemon Go is that technology can motivate people to action, especially when it's connected to other people. So I thought this was particularly telling, and is actually a great reflection of what Niantic is actually trying to do at its heart. We believe that with the power of technology, we can inspire people to go out and experience their real world. We can inspire them to make connections to others and look up and understand the communities around them. We actually believe that people are healthier when they go outside, when they have a reason to explore the outdoors with others, and that this social connection is actually mutually self-reinforcing. And it turns out that we knew all of this even before Pokemon Go, because we've lived it. We've lived it for the past 4 years with Ingress. So this is an Ingress event in Tokyo in July 2016. And here you can see several thousand people who showed up to a major Ingress event. They came from not only from all around Japan, but from all across Asia and the world to play together on the streets of Tokyo for a single afternoon. Just imagine that, right? Like people 14-hour flights just to come and play with both their strangers and friends just for a few hours. And how can we motivate people to do this? Well, I have to say, it feels truly incredible and a real privilege to be part of something that can actually make this kind of thing happen, especially when, at a time when the rest of the software industry seems to be focused on getting us to put on a pair of goggles and box ourselves up from the world. Not that there's not necessarily anything wrong with that set of technologies, but I do think that what we get to do is particularly unique and interesting. Instead, we've inspired people to actually go outside, go across their cities, go across countries and continents to meet and play with others. So in Ingress alone in the past 4 years, we've had hundreds of thousands of people show up to real-life events held throughout the world to play Ingress with others. And it turns out that the Surgeon General is right. By creating a game where you and your friends and your family and your newfound friends can all share and inhabit the same fantastical universe of Pokemon, we've inspired people to walk more than half of the way to Pluto through the end of August. So that's 4.6 billion kilometers. And we know from Ingress that this actually leads to much more. For the past 4 years, every week we've been getting stories of people who lost dozens, sometimes more than 100 pounds playing Ingress. We got countless stories of people who met playing Ingress and got married. We got dozens and dozens and dozens of pictures of people getting Ingress tattoos. And some of the most inspiring stories were people who made great strides in their social anxiety through Ingress. So let's go a bit into how all of this is accomplished. So at the most basic level, it starts with a mobile phone app that connects and links the player to both the world around them as well as an alternate vision around the world. Right? The key thing here is that all the data that is displayed in this world is consistent for all users. And on the left is Ingress, and on the right is Pokemon Go. You can see some common elements. There's an underlying map, but there are also geolocated game objects. I'll go a bit more into all of this later. But let's start with Ingress. So when you download Ingress, your phone becomes a window into an alternate reality surrounding us. First, you join one of two teams, either the Resistance, represented in blue here, or the Enlightened, represented by green. And next, you'll see portals. Now, these are real-world, publicly accessible locations, like the Eiffel Tower on the left, that are highlighted in your team's color, overlaid on a map of the real world. So if you're willing to get up and go visit them, you can go and capture them for your team and help take over the world, as long as you keep moving. So note that in Ingress, the way that you gather up energy in order to take over these portals are these little tiny points of light that are scattered around on the ground. As you walk, you collect these globs of energy, and those globs of energy become the core resource mechanic that allows you to interact with the portals. Once you capture once you capture these portals, you can begin to link them together. And once you link 3 portals into a triangle, you can actually create a field. And so you can actually see the links between portals as these lines, and fields as the areas of control under them. And by building successfully larger fields, you can begin to take over neighborhoods, cities, and countries. And finally, you can end up taking over entire continents and oceans. And so this picture shows that Ingress is truly a globe-spanning game on a single instance. Nothing shows that off better than the ability to create megafields that encompass massive fractions of the Earth's surface. So for the technically minded, consider what is happening here from like a latency and contention standpoint, right? Everybody playing from Milwaukee to San Diego and then past Vancouver, as soon as that field's created, within a few seconds, they need to see the game state updated. Everybody under that field should be able to open up their clients and see the same single consistent reality. It's an immense scaling problem with tight latency constraints because we want to have consistent game rules. So Likewise, in Pokemon Go, the game again centers on a representation of the player's surrounding environment. So the curated points of interest that we assembled for Ingress have now been repurposed as either gyms or Pokestops. And the Pokestops you can see as these little blue cubes. And the gym, there's one gym off in the distance. And then on the right here, you actually have a player battling at a gym. Now, we kind of inverted the resource model in Pokemon Go. Now you gather resources from the Pokestops and use those resources to catch Pokemon who spawn in the world as you travel from place to place. And the objective is to catch these Pokemon, train and level them, and then use them to take over gyms for your team. Again, the state of the world around you is consistent across everyone's game clients who are in the same local area. And as you take over a gym for your team, that change needs to be reflected in the mobile clients for everyone around you, up to about 1 kilometer away. So if somebody takes over that gym off in the distance and changes the color of it, we want that to be reflected in everybody's clients who are within that radius. So we have a self-reinforcing loop in both games that encourages travel, continued movement, and social interaction. So on the top is we begin the cycle with walking, where in Pokemon Go you encounter Pokemon, or in Ingress you gather XM, those little globs of energy. And then that walking should lead you to a destination that you can see on your map, either a portal, a Pokestop, or gym. And once you get to that destination, there's an action that you can perform, or set of actions that you can perform at that destination that changes the state of the destination, consumes or provides resources, and pushes you back into a walking cycle. And so we'll go over the key problems and pieces of data that are necessary to enable each element of this loop individually, and we'll dive a bit into the technologies that Niantic has used to solve these problems. So let's start with the walking. So the XM and Pokemon data are extremely numerous, and in order to provide a consistent play experience, they need to be populated worldwide. They also, so we have a need for rapid iteration of worldwide geodata, because we want to constantly be able to tune our algorithms, change our algorithms to repopulate and change that worldwide data until it has the right game balance. So this data needs to be contextually aware. So for example, you wouldn't expect to find a sand shrew show up more in Seattle than you would in Arizona. It's a very sandy looking Pokemon. So in order to get that kind of contextual awareness and be able to tune it, we want to be able to rapidly iterate on large, immense worldwide amounts of data within a matter of hours. Now, the other thing that we need to do, or the next thing that we need to do to empower this cycle, is to enable the real-time mutation of millions of players of data, millions of players worth of data. And this is not easy for a traditional relational database management system, right? The amount of people who are simultaneously hitting a single homed instance would be enough to crash any kind of naively single home system. So we need to have some sort of solution that can scale horizontally across a wide number of simultaneous player mutations. And finally, we need accurate, responsive geolocations. Note that the requirements here are actually much more stringent and much more difficult than the typical road navigation application, right? When a car is driving along a road, the GPS software has the benefit of large deltas as a function of time, right? Which means that the tolerances on errors can be quite a bit greater than if you were just walking along. In addition, a lot of the roads are prior for the road navigation software, so they can correct for errors by snapping you back to where they think you should be. Whereas, if you're wandering through a large grassy field, that's not necessarily the case. So how do we solve all of this? So For the rapid iteration of worldwide geodata, we use MapReduce. And to be specific, we use a particular implementation called Cloud Data Flow to satisfy our need to rapidly iterate and change our geodata. Now, within Google, this framework was actually called Flume Java, if you remember any of the if you've ever seen any of the academic papers on it. And what it does is that it abstracts away the basic serialization and management of the map and shuffle and reduce steps by instead having you program in abstract parallel computing functions, right? So instead of having to, wire together a piece of code that says map and then serialize my data and then send it to a specific set of machines, instead, Cloud Data Flow allows you to program in parallel mapping or parallel keying, rekeying, or parallel combination functions. These functions can then be mixed and matched and reconfigured quickly and then deployed onto Google's automatically scaling infrastructure for running MapReduces. So Cloud Data Flow takes the data transformation steps, appropriately merges and combines steps that can occur together into an efficient series of map, shuffle, and reduce steps, and then executes it on the automatically provisioned Google infrastructure. As a result, we could rapidly iterate on different versions of our spawning algorithms and recrunch the entire world's geodata in a matter of hours. Because the pipeline components are abstracted at a data transformation level, we could divide, combine, and experiment with different integrations of data rapidly without having to worry about the underlying pipeline implementation or scaling details. So in the morning, I could look at a map with my engineers and say, that looks great, but I really think that our algorithms should infer that this place here might need a few more of this kind of spawn. If the algorithm hasn't done that, we haven't nailed it, and by lunch, we would have it showing up. Pardon me. So next, in order to mutate millions of players' data simultaneously in real time, we need a data store that is efficient to provision and is scalable all the way from development to worldwide deployment. And so cloud-based distributed and NoSQL data stores, such as Google Cloud Data Store, achieve this for us. For a kind of data schema where there are not significant table-wide locks necessary, such as individual player data, it makes sense to go with an optimistically concurrent distributed data store, since we can tolerate eventual consistency when querying along the table. In any case, if we actually wanted to perform non-trivial queries against the data, we wouldn't use traditional relational secondary indices. We would just throw all the data at Cloud Data Flow. Finally, we need accurate responsive geolocation. And we have built upon the native platform implementations with custom-written dynamic BaseNet that performs sensor fusion on the device and provides on device and provides the best experience to our users. So let's dive into the next component of the cycle. Next component of our loop is destination. How do we find what we're looking? Oh, sorry. How do we find the destination? Is the first question, right? And then what is the destination is the next question, and finally, how do you get to the destination is the last one. And so the first thing that we need is a scalable, consistent, real-time geospatial query. So to define what that means in kind of simpler terms, it really is the heart of the game. It means that when somebody changes the world around them, we need to enable the mobile clients for everybody else around them to perform a roughly 1 kilometer query against the server and see that same change reflected in their clients. We also need a set of destinations themselves. These are locations that need to be publicly accessible and walkable, but ideally also interesting and relevant landmarks that players will connect to and remember at a visceral level. And finally, we need to render a representation of the road and walkways map. Unlike typical mobile navigation applications, it needs to be rendered in 3D rather than 2D so that it can be visually attractive and consistent with the theming and overall product presentation of our game client. So we solved that with two sets of technologies and a data set. So the first set of technologies is quite important. We built highly scalable custom geospatial query logic on top of scalable container instances living on a Kubernetes cluster. So what does all that mean? So for those of us who were Googlers a few years back, the key to Google's ability to deploy applications quickly at scale on their data center infrastructure was a system called Borg. So Borg basically took applications written by engineers at Google and with some amount of configuration would automatically deploy and scale it along the data center infrastructure and deconflict, well, most importantly, deconflict resource requirements for various applications so that the data center could run at very high levels of utilization. So Kubernetes is actually the modern open source implementation of that system. It is Google's Borg made available for public use. And that service is implemented on Google Container Engine. So for those who are unfamiliar with what containers are, you can essentially regard them as bare bones isolated Linux instances that achieve isolation at a OS level rather than at a hardware emulation level, right? So you may have heard of virtual machines. Virtual machines often work by emulating all of the hardware interfaces, but a container actually is much more lightweight than that. It can achieve isolation so long as the kernel of the operating system permits it at a kind of file system root level, right? So instead of partitioning virtual hardware resources, you just partition virtual Linux file system roots. And as a result, the incremental resources necessary to host incremental isolated container on a given machine is minimal, since the deconfliction is all achieved by the kernel. So the result is a highly flexible, scalable architecture where we can mix and match isolated services, mix and match them with publicly available containers, and co-locate them on machines as we desire to achieve the scaling and latency characteristics that are necessary to build this custom geospatial query logic. It turns out that the result is that Pokemon Go actually runs on the world's largest Kubernetes cluster ever. So secondly, we have our points of interest. For the first couple of years of Ingress's life, we built out an amazing data set of the world's most interesting foot-accessible public locations, and they were all submitted by a large fraction of them were submitted by our users. Our users were actually interested in making Ingress an even better game, and we solicited their submissions of potentially valid locations and figured out which ones were the best ones and put them into the game. So the result is that we have a data set of 5 million or so curated locations worldwide that we now use as the basis of our points of interest in Pokemon Go. The last thing we need is a representation of the underlying streets, walkways, and buildings to orient our users and navigate them to destinations in the game. We achieve this with a custom map tile rendering engine that caches and generates map tile geometry in 3D on the client and presents it to the game application layer to be skinned appropriately for in-game presentation to the user. Let's see if I can. So finally, the last piece of the loop is the shared action piece of the loop. We need two things here. The first is scalable cross-player single entity mutations. So what does that mean? That means unlike the previous data store mutation case that I illustrated, where you basically scaled horizontally across many millions of players simultaneously, now you have a single Pokestop gym or portal, and somebody wants to act on it, right? Maybe sometimes somebody wants to put a lure on it. Others might want to battle Pokemon on a gym, or other members of a team with resonators and XMPs and Ingress to take over that location. But this creates a different kind of scaling problem. It creates a vertical scaling problem because many people are operating on the same entity at once. So what do we do about dozens or hundreds of people attempting to mutate the same geo entity at once? And then finally, the last thing that we need is that attractive cross-platform user interface. This is, after all, a game, right? And we need to present, we want to show off our assets in 3D and help preserve the user's sense of disbelief that they're actually playing in a virtual world overlaid on top of the real one. And in addition to that, present potentially complicated 2D and 3D user interfaces that we can rapidly iterate on in a cross-platform manner. So how do we solve this set of problems? Sorry. So we have custom deconfliction logic that we layer on top of the NoSQL data store. And again, the key here is our ability to build and scale that logic indefinitely, nearly indefinitely, using Kubernetes and Container Engine. And then secondly, we achieve our attractive 3D interface that can work on both Android and iOS using the Unity 3D game engine. This allows us to integrate both 3D information as well as attractive 2D interface tools without having to write the whole game twice. So let's put all of this together into an architectural diagram. So on the left, we have the mobile client, which is written in C# on top of the Unity 3D game engine. And it contains both our querying and caching logic for geospatial objects as well as map tiles used in rendering the client. These read and write from Niantic server logic hosted on the world's largest Kubernetes deployment, spanning tens of thousands of CPU cores. And as before, we write to custom logic for both player data and geodata, and then read from a custom spatial query service. Finally, that server logic talks to an underlying NoSQL data store as its ground source for truth, and conducts its transactions against that data store to make sure that the data remains consistent for both the player and geodata. And on the back end of that data store, we can process massive fractions of that data store within hours simply by writing MapReduces using Google Cloud Dataflow. So with the architecture stuff done, I want to talk for a minute about just how much, how well this actually scaled. And I think the best way to actually to illustrate that is to walk you through how the launch went. So we finalized the game client before the July 4th weekend, and I got the team to go relax with their friends and families and watch some fireworks on Monday. And then we all came back and went right into the teeth of it. First, soft launching in Australia and New Zealand on July 5th. Now, so here's the point at which I will admit to being the guy who wrote the initial resource estimates for our friends at Google so that they would know how much to provision and might ask for. And I thought I did those estimates in a fairly reasonable and sane way. Knowing that we had an immensely popular and beloved intellectual property and a proven track record of success with Ingress, I looked at the market and growth curves for the top end of mobile games and gave ourselves a little more margin for how they typically launched, and handed an expected number as well as a ludicrous 5x number over to Google for provisioning. And for a glimpse of exactly how that went, you can see the orange was my expected number, the red was my ludicrous number, and the green was the actual traffic. So going back to the calendar, we knew we had something special on our hands when we nearly exceeded our peak worldwide capacity on what I thought would be less than 5% of the total eventual worldwide install base in Australia and New Zealand. So that was the point at which we called in the cavalry, and here's where I do really have to thank our friends at Google, because we're a relatively small startup operating on top of their infrastructure, and we were able to scale continuously, for two reasons. One, that I believe we wrote quite robust code that was algorithmically sound, but also because they could scale their services underneath us rapidly as we needed to grow. And so I think it's a testament to the scalability of their systems as well as the robustness of our code that they could simply scale the underlying services without ever taking a peek inside our code base. And we just had to beat out the occasional scaling bug in our code. So I'm proud to say that while there's several like n-squared like problems in all these custom query logic things I've talked about, at no point did anything fundamental to our design become restrictive to our growth. All of our latency and stability issues were the result of much more prosaic concerns familiar to any engineer who works with a high QPS service, like naive implementations of mutexes. So this means that you mostly spend most of your time taking heap dumps, looking for the fact that like a bunch of your threads are hung up on one silly point. You make a one-line fix, you redeploy everything, and you move on. The only difference from most people who have to beat down these kind of problems and bugs and us is that we essentially did it while riding on top of a rocket ship. We were riding a massive wave of momentum and wanted to launch as far and as wide as possible while the world was watching us and eagerly anticipating Pokemon Go. So as fast as we reasonably could, we opened our doors to Europe in the week after our US launch, followed by Japan the week after. And by early August, we'd gotten through our initial rollout targets through Latin America and Southeast Asia. So just one more time, here's the perspective on that series of launches. And just to be clear what this represents, it's the net number of transactions that we were pushing to the cloud data store NoSQL database layer under us, just to give you an idea of just how far off we were from our initial estimates and how fast we were able to grow. But the work that we put into thinking through carefully how our system could scale paid off. When just 2 weeks after our US launch, we were able to have another massive launch in Japan without incident. So with the Pokemon Go launch behind us, I want to talk a bit about Niantic's future. So we believe that we have conclusively demonstrated that augmented reality is as much about the shared world state overlaid on the real world as it is about immersive hardware devices that are still on the horizon. We know that those immersive hardware devices are coming, and that bright and talented people are working incredibly hard to make them a reality. But the market reality for us right now is that what everybody has in their pocket is a cell phone. But even within those constraints, we can make a world where people believe that an awesome, fantastical universe is overlaid on top of the real world because everybody around them is sharing the same state and believes it too. In the present, we can drive home that point with simple camera and gyro-assisted AR, like the gym battle that you see on the right. But that's a glimpse into where the future, but that's just simply a glimpse into where the future can go with more immersive hardware devices. Now, furthermore, we believe we can still innovate in alternative complementary game modes that bind you to the virtual world while keeping you fully immersed in the real one. That's the goal of the Pokemon Go Plus, or wearable device that's shown on the left. It buzzes and flashes when Pokemon and Pokestops are nearby, and you can catch or collect them with the press of a button. This is definitely not as complex a game as the in-phone experience, but a truly complementary mode that allows you to play the game from a totally different perspective. And so with our massive install base and proven leadership in the field, we expect to continue to innovate and drive novel hardware integrations. So we have every intention of making the long-term investments and pushing forward with every product we create to get closer and closer to a future where the augmented reality means a seamless integration of the outside world, the people around you, and the virtual world overlaid within it. So going back to the beginning, we really believe that Niantic's products will bring tangible benefits to people's lives above and beyond their entertainment value. It'll get them and their families to get outside walking together, living longer and healthier lives. We believe that we hope to continue to forge and strengthen interpersonal relationships, both the friends that you take on these journeys and the ones that you'll meet on them. And finally, we'll continue to integrate people into their communities, rebinding our social fabric, inspiring people to improve the outside environments and world around them. So finally, I want to thank a few people at the end here. First, I want to thank Professor Jeff Volker for inviting me to speak here. The last time I spoke for Jeff was at the end of his CSE 125 game design and development class 12 years ago. Back then I had a full head of hair, and I wore a full tuxedo for that talk. So I'm not sure if my current appearance gives me any more credibility, but his mentorship all those years ago has had a direct impact on me and on these games coming to fruition, so I want to thank him for that as well. Secondly, if I haven't plugged their products enough, I do want to thank the Google Cloud Platform team, whose assistance and cavalry charge in our time of need to scale up every aspect of the platform to unheard of levels made this all possible. And finally, my CEO, John, makes a point every time he speaks to publicly thank his engineering team. I'd very much like to do so as well. A few incredibly passionate, smart engineers essentially spent the entire month of July constantly awake to get this out to the world, and they deserve an immense amount of recognition for that achievement. And so, finally, for the undergrad and grad students in the audience, none of this would have been possible without the core algorithmic abilities I gained at UCSD. So I know that you have the algorithmic chops that are needed. So if you're interested, we're looking for bright, enthusiastic recruits who believe in what we're trying to do. And you can get a hold of us at universities@nianticlabs.com. Thank you.